Welcome back to the deep dive. We're here to sift through the noise, dig into the sources, and pull out the essential knowledge you need.
That's the goal.
And today, we are really diving deep into reinforcement learning. It's the foundation for so much of the AI progress we're seeing lately.
It really is. And our source material for this one is, well, it's basically key excerpts from the book on the topic. A foundational text that lays out the whole landscape of modern RL.
Okay.
It covers the algorithms, the core principles that drive everything from, game-playing AI like AlphaGo to robotics, even shedding light on how our own brains might learn.
So our mission today is to unpack all that. We want to really get a handle on that core loop, the agent interacting with its environment.
Right.
How does it learn? This trial and error thing to maximize some kind of reward. And what are the different ways, the different strategies these systems use? We'll dig into the key ideas, maybe some of the challenges, and look for those interesting connections.
Definitely. And actually, before we jump into the technical side, it's worth mentioning the dedication in the book
Yeah.
to A. Harry Clough.
Ah, right. That wasn't just a standard dedication, was it? His ideas were pretty central.
They really were foundational. Clough was a senior scientist looking into machine intelligence, neurophysiology, and he had a real critique of how people were thinking about intelligence back then.
What was his main point?
He wasn't buying into models that were just about equilibrium seeking, systems that just try to minimize errors or get back to some baseline state.
Like just fixing mistakes or maintaining stability, like homeostasis in biology.
Exactly. Like pattern classification minimizes errors, homeostasis keeps your body stable.
Yeah.
Clough thought that missed something crucial.
Something more active.
Precisely. He argued that systems that maximize something, that actively pursue a goal, a signal, are fundamentally different.
Yeah.
He believed that this drive to maximize was the key to understanding how real intelligence, natural or artificial, adapts and learns in complex situations. It goes beyond just reacting.
And that idea, maximizing a signal, that's basically the heart of reinforcement learning, right?
It absolutely is. That's the core pursuit.
And he didn't just theorize, he actually helped get the research started.
Yeah, critically.
Yeah.
Clough was instrumental in getting the early funding back in the late 70s from the Air Force Office of Scientific Research, AFOSR.
For that project at UMass Amherst.
That's the one. It was specifically focused on that intersection, neuroscience and AI. And that's where the authors of this book first collaborated, working on what eventually became modern RL.
Right.
Later, the NSF also chipped in significantly.
Yeah.
So yeah, his vision, his advocacy, absolutely vital.
So RL has this dual heritage baked in from the start. It's tackling AI and machine learning problems computationally, but it's also deeply intertwined with ideas from psychology, from neuroscience, that link how we build smart machines and how maybe brains actually work. That seems like a recurring theme.
It really is. It's a fertile ground. Ideas flow back and forth between the fields.
Okay, let's dive in then. Let's start right at the core. Reinforcement learning. What's the absolute fundamental idea?
So basically what it boils down to is this. You have an agent. Think of it as the learner or decision maker. It exists in an environment. And it learns how to act, how to behave optimally, purely through trial and error.
Trial and error. How does that work?
Well, the agent takes an action. The environment responds to that action, maybe changes its state, and it gives the agent some feedback. Crucially, this feedback is a number accord, a reward signal.
A numerical reward. Positive for good things, negative for bad.
Could be positive, negative, zero. And the agent's whole goal is to learn a strategy, what we call a policy, that maximizes the total amount of reward it collects over the long run.
And this interaction, the source calls it the agent-environment interface. It's like a continuous loop.
Exactly. Picture this cycle. At any point in time, the agent sees its current situation, its state. Based on that state, it picks an action, it performs the action.
And then the environment reacts.
Right. The environment transitions to a new state, and it hands back that numerical reward. And this just keeps going. State, action, reward, new state, action, reward. This whole sequence is the agent's experience.
Okay, so it's constantly interacting, constantly getting feedback, and the aim isn't just the immediate reward, it's the total reward down the line. That's the return.
Precisely. The return is what the agent tries to maximize. Now, how you define that return depends a bit on the task.
How so?
Well, some tasks are episodic. They have a clear start and finish, like playing a game of chess or a maze run. The episode ends when you win, lose, or reach the goal.
Okay.
For those, the return is usually just the simple sum of all the rewards you got from now until the end of the episode. We call that the undiscounted return.
Makes sense. Just add up all the points you scored in that game.
Exactly. But then you have Continuing tasks, these just go on and on, theoretically forever. Think of like a climate control system or maybe process control in a factory. There's no natural endpoint.
So you can't just sum the rewards forever. That would blow up.
Right, it could go to infinity. Not very helpful. So for continuing tasks, we use what's called a discounted return. We introduce a discount factor, gamma, usually written as gamma.
Gamma.
Okay, it's a number between 0 and 1. And the idea is that rewards you get further in the future are worth less than rewards you get right now. A reward 1 step away is multiplied by gamma, 2 steps away by gamma squared, 3 steps by gamma cubed, and so on.
So future rewards get progressively smaller weights.
Exactly. The return is the sum of these discounted future rewards. This keeps the total sum finite, even if the task goes on forever. And it also, kind of intuitively, makes the agent prioritize getting rewards sooner rather than later, assuming gamma is less than 1.
So if gamma is close to 1, the agent is very farsighted, cares a lot about the future.
Yep. And if gamma is closer to 0, it's more short-sighted, focused on immediate rewards.
Okay. But the core idea is always maximizing that expected cumulative reward, discounted or not. And the learning happens through
Trial and error. Fundamentally, the agent tries stuff, sees what happens to the state change and the reward, and over time, it learns which actions in which states tend to lead to higher total rewards.
that trial and error idea feels very fundamental. You mentioned it has roots outside computing.
Oh, absolutely.
Yeah.
You really can't talk about this without mentioning the psychology connections. Edward Thorndike, back in the late 1800s, early 1900s, with his cats in puzzle boxes.
Right. The law of effect.
Exactly. He saw that if an action was followed by something satisfying, the cat was more likely to do it again in that situation. If it was followed by something annoying, it was less likely. That's basically reinforcement learning in a nutshell. Actions leading to good outcomes get reinforced.
And the term reinforcement itself, that also came from psychology. Pavlov.
Yeah, the source points that out. Seems like Pavlov used it first in the English translations of his work around 1927. He used it to describe how a conditioned response gets stronger because a reinforcer like food is timed appropriately with some other stimulus or response.
But there was a nuance there, wasn't there? About what counts as true reinforcement.
Yes, a really important point psychologists made. For something to be a proper reinforcer, the change in behavior it causes has to stick around after the reinforcer is gone.
So it can't just be a temporary boost.
Right. If it just grabs attention or makes the animal perform better while the stimulus is there, but doesn't lead to lasting learning, a persistent change in how likely the behavior is, then it's not reinforcement in the technical sense. It's about learning. Persistent change.
Okay, so trial and error, rewards, maximizing return, psychological roots. But this leads to a big problem. The credit assignment problem.
Ah, yeah. Marvin Minsky pointed this out way back in '61. It's a classic. If an agent does a whole sequence of things and then way later gets a reward or maybe a penalty, how does it know which specific actions in that long sequence were actually responsible?
Right. You play a whole chess game, make dozens of moves, and you win. Was it that brilliant move early on, or the okay moves just before the end? How do you assign credit?
Exactly. The reward is often delayed, and it's often sparse. You don't get feedback after every single move. This is a fundamental difficulty. And really, you could say that all the algorithms we're going to talk about are, in some way, shape, or form, trying to solve this credit assignment problem. There are different ways to figure out how to distribute that credit or blame back through time to the right states and actions.
That's a great way to frame it. The whole field is kind of obsessed with assigning credit properly. Okay, so let's unpack the machinery inside the agent. What are the key pieces it uses?
Okay, so we've got the agent and the environment interacting. The agent is in different states. That's its perception of the situation. And from each state, it can choose from a set of possible actions.
And its strategy for choosing actions is its policy.
Correct. The policy, usually written as PRAY, defines the agent's behavior. Formally, it's often a map from each state to the probabilities of picking each possible action in that state. It tells you how the agent acts.
But just acting isn't enough. It needs to know if its actions are good. It needs to predict future rewards. That's where value functions come in.
Yes, value functions are absolutely central to most RL approaches. They estimate future rewards. They basically answer the question, how good is it for me to be in this situation?
And the source mentions two main kinds.
That's right. First, the state value function, written V. This estimates the expected total future return if you start in state ties and then follow policy from that point onwards.
So if I'm here and I stick to my current plan, what reward total can I expect?
Exactly. Then there's the action value function, QSA. This one's a bit more specific. It estimates the expected return if you start in state S, take a specific action A, and then follow policy after that.
Ah, so that tells you the value of taking a particular action now.
Precisely. It answers, if I'm in state S and I choose action A right now and then follow my plan, what reward total can I expect? This Q function is often really useful for making decisions because you can compare the Q values for different actions in the current state. And these value functions, V and Q, are what the agent learns to estimate from its experience.
So it's learning how good its current policy is. But usually the goal isn't just to know how good the current policy is, it's to find the best policy, right?
Exactly. That brings us to optimal value functions and optimal policies. The optimal state value function, VT, is the maximum possible expected return you can get starting from state S no matter what policy you use. It's the theoretical best case scenario for that state.
And similarly for actions.
Yep. The optimal action value function, QSA, is the maximum expected return you can get if you start in state S, take action A, and then follow an optimal policy thereafter.
And an optimal policy is just any policy that achieves these maximum values.
That's right. There might be more than one optimal policy, but they all share the same optimal value functions, V and Q. And here's the crucial part. If you know the optimal action value function, Q, then finding an optimal policy is easy. In any state S, you just pick the action A that has the highest QSA value.
So learning Q is often the main goal because it directly tells you the best action to take.
In many methods, yes. If you have Q, you essentially have the solution.
Okay, how do these values relate to each other over time? Like, how does the value of where I am now connect to the value of where I might end up next? Is that the Bellman equation stuff?
Absolutely.
Yeah.
The Bellman equations are fundamental. They express a consistency condition that true value functions must satisfy. They basically break down the value of a state or state action pair into two parts: the reward you expect to get immediately and the discounted value of where you expect to end up next.
The source had a diagram for the Bellman equation for V. Can you sort of paint a picture of that?
Sure. Imagine you're in a state S. That's the root node. Now, your policy tells you the probability of taking different actions A from state S. So from S, you have branches going out to action nodes A, weighted by the probability AS.
Okay.
Now, for each action A you might take, the environment has its own dynamics. It will transition you to some next state S and give you a reward R with a certain probability, PSS, RSA. So from each action node A, you have branches going out to possible outcome nodes, SR, weighted by the environment's probability.
Right.
The Bellman equation for VS is that the value of state S is the average over all those possibilities. You average over the actions A you might take, according to Wei, and the resulting states and rewards SS, according to the environment dynamics. What you're averaging is the immediate reward R plus the discounted value of the next state.
So the value here equals the expected immediate reward plus the expected discounted value of the next place I land.
Exactly. It's a recursive relationship. The value of a state depends on the values of the states you can reach from it. These equations are the bedrock. Methods like dynamic programming use them directly if you know the environment's model. And RL methods use them as a template for updates, even without the model, learning from samples of SARS.
And there are similar equations for the optimal values, V and Q.
Yes, the Bellman optimality equations. The main difference is that instead of averaging over actions according to a policy, you take the maximum value over all possible actions. That max reflects the fact that an optimal policy will always choose the action leading to the best possible outcome.
Okay, policy is behavior, value functions predict reward, Bellman equations link them. But the agent learns by trial and error. How does it decide whether to stick with what it thinks is best right now versus trying something new just in case it's better?
Ah, yes. That's the classic exploration-exploitation dilemma. It's one of the absolute core challenges in RL.
Explain that a bit more.
Okay, so the agent wants to maximize its total reward. To do that, it needs to exploit its current knowledge. It should take the actions that, based on its current estimates, it believes are the best, the ones with the highest expected value.
Makes sense. Do what seems best.
But what if its current estimates are wrong? What if there's a fantastic action out there it hasn't tried very much, or at all? To find those potentially better actions, it also needs to explore. It needs to try actions that don't currently look like the best, maybe even actions that look bad, just to gather more information and improve its estimates.
And those two things, exploring and exploiting, are fundamentally at odds.
Exactly. If you only exploit, you might get stuck doing something that's pretty good, but miss out on something much better because you never tried it. You get stuck in a local optimal.
Well, if you only explore,
Then you're just acting randomly all the time. You'll find the good stuff eventually, maybe, but you'll never capitalize on it. You'll perform poorly because you're not consistently choosing the best actions you found.
you need a balance. But finding the perfect balance sounds tricky.
It is. Theoretically, the optimal way to balance depends on how uncertain your estimates are, how much time you have left, the environment's structure. Calculating it perfectly is usually impossible. So in practice, we use heuristics, different strategies to manage the trade-off.
Like, epsilon greedy, that sounds familiar.
Yes, OIGRI is a very common and simple approach. It works surprisingly well. The idea is, most of the time, say with probability 1, where epsilon is a small number, the agent exploits. It chooses the action with the highest current estimated value.
Okay.
But with a small probability, it ignores its estimates and explores. It just picks an action completely at random from all the available options.
So it mostly does what it thinks is best, but occasionally takes a random punt.
Exactly. That little bit of random exploration ensures that over the long run, it keeps trying all the actions and won't get permanently stuck. It keeps gathering information.
And maybe you decrease epsilon over time. Start more exploratory, then become more greedy.
That's a common refinement, yeah. Annealing epsilon. Start high, explore a lot, then as your estimates get better, reduce epsilon to exploit more.
The source also mentioned another trick. Optimistic initial values.
Right, another neat idea. Instead of starting your value estimates at 0, which might be a reasonable default,
You start them really high.
yeah, you initialize all the action values optimistically, maybe to the maximum possible reward or even higher. Now, if the agent is greedy, or O-greedy, it's naturally drawn to actions with high estimated values.
So if all the initial values are high.
It gets encouraged to try all the actions because they all look promising initially. It wants to find out if they really are that good. When it tries an action, it gets a real reward, updates the estimate, which will likely go down, and moves on.
So it kind of tricks itself into exploring everything at the beginning.
Pretty much. It explores because it's chasing these initially inflated values. Eventually, the values settle down closer to reality, and the exploration driven by optimism fades. The source showed that figure 2.3, on a simple bandit problem.
Yeah, the 10-armed bandit.
Right. The purely greedy agent got stuck pulling a suboptimal arm. The A-greedy agent did better because it kept exploring. But the optimistic greedy agent, the one starting with high values, explored intensely at first, quickly found the best arm, and actually outperformed the greedy one in the long run on that problem.
Because it did its exploration efficiently up front.
Exactly. It's a powerful demonstration for certain kinds of problems, especially stationary ones, where the best action doesn't change. Once you find it, you just exploit. But, as the source points out, if the environment can change, you still need ongoing exploration like iGreedy provides. Optimism alone won't cut it then.
Okay, managing exploration exploitation is crucial. Let's zoom out again. The big architectural split. Model-free versus model-based methods.
Right. This is a major way to categorize RL algorithms. It's all about whether the agent learns and uses an internal model of how the environment works.
Let's break down model-free first. What does that mean?
Model-free methods learn value functions or policies directly from experience without trying to build an explicit model of the environment's dynamics or reward function. They don't try to predict, if I do action A in state S, what specific state S will I end up in, and what reward R will I get.
So they're more like reactive learners, learning stimulus-response mappings.
Kind of, yeah. Think about learning to ride a bike. Most people don't build a detailed physics model in their head. They just try things. Lean this way, pedal like that. If they start to fall, negative reward signal, they adjust. They learn the mapping from sensations, state, to muscle movements, action, directly through the consequences, reward falling. That's the spirit of model-free learning.
Okay, so what about model-based methods?
Model-based methods do the opposite. They explicitly learn a model of the environment. They learn to predict the transition probabilities, PSS, RSA, the probability of ending up in state S with reward R, giving you're in state S, and took action A.
And what do they do with this model?
They use it for planning. They can simulate interactions with the environment internally using their learned model. They can ask what-if questions. What if I tried this sequence of actions? What states and rewards does my model predict? They generate simulated experience and use that experience to update their value functions or policy, often alongside learning from real experience.
So they can sort of think ahead using their internal simulation.
Exactly. That's the key benefit of planning.
What are the trade-offs then? When would you use one versus the other?
Well, model-free methods can be simpler, algorithmically. You don't have the potentially complex task of learning and storing an accurate world model. They might also be better if the environment is just too complex to model well, or if the model you learn might be inaccurate. They learn directly from what actually happened.
And model-based, the
Yeah.
advantage is
Data efficiency is a big one. A learned model allows you to generate potentially vast amounts of simulated experience from relatively little real-world interaction. This simulated experience can fuel learning much faster. Imagine learning a game. Playing one real game gives you one trajectory, but a model might let you simulate thousands of variations from that one game's data.
so they can learn faster with less real data.
Often, yes. They can also potentially adapt more quickly if the environment changes, if that change is captured by updating the model. They can then replan using the new model without necessarily needing to experience all the consequences of the change directly in the real world first.
It seems like a pretty fundamental difference, but the source mentioned they still share some core mechanics.
They do. Even though one uses a model and the other doesn't, both types of methods very often rely on computing value functions. And the way they update these value functions typically involves backing up values using information from future states, real or simulated, to update the estimate for the current state. That core idea of propagating value information backward is common to both.
Okay, let's delve into the model-free world first. Section 5 covers Monte Carlo, MC, and temporal difference, TD learning. These seem foundational.
Oh, absolutely. Two major families of model-free algorithms. They differ primarily in how they estimate values and when they update them. Let's start with Monte Carlo.
What's the MC approach?
Monte Carlo methods learn only from complete episodes. The agent has to run through an entire episode, from the start state all the way to a terminal state. Only after the episode is finished does it have the full sequence of rewards.
So it has to wait until the end of the game, say, to learn anything.
To make it update based on that episode's outcome, yes. To estimate the value of a state S, MC methods look at all the episodes where state S was visited. For each visit, they calculate the total return, a sum of rewards, received from that point onwards until the episode ended. Then they simply average these returns across all the visits to estimate VS.
Okay, so it's based on the actual complete return observed after visiting a state.
Exactly. The source mentions variations like first visit MC, only average returns after the first time S is visited in an episode, and every visit MC, average returns after every visit to S in an episode. The core idea is averaging complete sample returns.
How do you use MC for control, for finding the best policy?
You iterate between policy evaluation, estimating action values, Q, using MC, and policy improvement, making the policy greedy with respect to the current Q estimates. A method called Monte Carlo ES, exploring starts, does this.
Exploring starts, what's that?
It's an assumption that, to ensure you learn the value of all actions, every state-action pair has some chance of being the starting point of an episode.
That sounds a bit restrictive. You can't always control where you start.
Exactly. It's often an unrealistic assumption. So to do MC control without exploring starts, you usually need off-policy learning.
Off-policy, meaning you learn about one policy while following another.
Precisely. You might follow a behavior policy that explores a lot, like choosing actions randomly, to generate experience. But you want to learn the value function for a different target policy, like the optimal greedy policy.
But the experience comes from the exploratory policy. How do you adjust for that mismatch?
That's where important sampling comes in. When you get a return G following an episode generated by the behavior policy B, you need to weight that return based on how likely that sequence of actions was under the target policy compared to how likely it was under B.
So you calculate a ratio of probabilities.
Yes, the important sampling ratio. It's the product of the probabilities of taking each action in the sequence under B, divided by the product of the probabilities under B. This ratio corrects for the fact that the data came from a different policy. If the behavior policy did something the target policy would almost never do, that episode gets a very low weight for updating the target policy's value.
The blackjack example in the source illustrated this. Example 5.4, figure 5.3.
Yes, that's a good one. It showed estimating the value of a blackjack hand using MC. The behavior policy was simple, maybe random, while the target was a better strategy. The figure compared ordinary importance sampling, just using the ratio, with weighted importance sampling using a weighted average. Weighted importance sampling was shown to be much more stable, less variance, especially early on.
And ordinary importance sampling could be unstable. There was another example, 5.5, figure 5.4.
Right, on a very simple MDP. Ordinary importance sampling can have infinite variance if the behavior policy can take actions the target policy would never take, zero probability. This means it might not converge properly. Weighted importance sampling is generally preferred for off-policy MC because it has lower variance, although it introduces a small amount of bias.
Okay, so MC, complete episodes, actual returns, needs importance sampling for off-policy. How does temporal difference, TD learning, differ?
TD learning is the other giant in model-free RL, and arguably more influential in many ways. The massive difference is that TD methods do not wait for the end of an episode. They can learn online after every single step.
How? If they don't have the final return?
They bootstrap. That's the key term. They update their value estimate for a state based on the immediate reward they receive, plus their current estimate of the value of the next state they land in.
Ah, so they update a guess based on another guess.
Exactly. The simplest version, TD0, updates the value V0 after transitioning from state S to S0 and receiving reward R0. The target for this update isn't the full final return euro, but rather R0 plus VSU. It uses the immediate reward plus the discounted current estimate of the next state's value.
How does that compare to MC and, say, dynamic programming?
It's a neat comparison. MC waits for the full actual return sample, G. DP, which needs a model, calculates the true expected value using the values of all possible next states. TD does a bit of both. It samples the immediate rewarder R0 and the next state S0, like MC, but then it bootstraps using the estimated value V S0, like DP, in spirit, using an estimate instead of a true expected value.
So it combines sampling from experience with using its own learned estimates.
Precisely. That's why it can learn online and from incomplete episodes.
What's the actual update rule for TD Euros?
VSU gets updated towards the target. The update is VS, Dairodo, plus EVS0, VS. That term in the square brackets is super important.
The TD error.
Yes, the TD error, often written as a delta. It's the difference between the bootstrapped estimate of the value plus OVS and the current estimate. The update nudges the current estimate VS0 in the direction of this error, scaled by a learning rate, O alpha.
This TD error signal pops up everywhere in RL. And the source mentioned batch TD0. What's that about?
Batch updating means you collect a whole batch of experience, and then you repeatedly sweep through that data, applying the TD updates until the value function converges for that specific batch. The interesting thing about batch TD0 is that it converges to something called the certainty equivalence estimate.
Certainty equivalence.
It means it finds the value function that would be exactly right if you first built the best possible model of the environment based only on that batch of data, using maximum likelihood to estimate transitions and rewards, and then solve for the value function using that estimated model, like with DP. It's the optimal solution given the data under the TD0 update logic.
Okay, so TD can estimate values by bootstrapping. How to use it for control, to find policies?
Same idea as with MC. You apply the TD prediction idea to action values, Q values, and combine it with policy improvement. This gives rise to algorithms like SARSA and Q learning.
SARSA. That's on-policy TD control.
Yes. SARSA stands for State Action Reward State Action. It learns the action value function, QSA, for the policy the agent is currently following, e.g. A greedy. When the agent is in state SU, takes action AU, gets reward RO, and lands in state S0, it then chooses its next action, AURO, using the same policy. The update for QS0 plus RO uses the value of this next action A euros. QS0, A euros, plus QS euros, R euros, A euro, QS.
So the update depends on the action the policy actually selects next.
Exactly. It learns the value of acting according to the current behavior policy.
And Q learning, that's the famous off-policy one.
Right. Q learning is designed to learn the action value function for the optimal policy. Q directly, even if the agent is behaving differently, e.g. following an or greedy policy to ensure exploration.
How does it manage that off-policy learning?
The trick is in the update target. When updating QS0, Q learning doesn't care about which action A euros the behavior policy actually chose next. Instead, it looks at the state S euro and considers the value of the best possible action it could take from there, according to its current estimates. The update is Q euros, QSU plus QS euros plus MES, QS euros.
Ah, the max over A. It assumes optimal action will be taken from the next state, regardless of what the agent actually does.
Precisely. That max operator is what makes it off policy and drives the learning towards the optimal Q function Q. The backup diagram for Q learning in figure 6.4 shows the update pulls value from the maximum action value in the next state. SARSA's diagram would show it pulling value from the actual next action taken.
What about expected SARSA?
Expected SARSA is another TD control method. It's sort of a hybrid. Like SARSA, it considers the agent's current policy. But instead of using the Q value of the single action A arrow that was actually sampled next, it calculates the expected value over all possible next actions, weighted by their probabilities under the current policy. The target becomes R euro plus Q at euros. This can reduce variance compared to SARSA because you're not relying on a single sample next action, but it requires knowing the policy probability.
Okay, now there was a potential issue mentioned with Q learning specifically, maximization bias.
Yes, this is important because Q learning uses that max operator over its own potentially noisy Q value estimates. It can systematically overestimate the true action values.
How does that happen?
Imagine you have several actions, and your Q value estimates for them are noisy, sometimes a bit high, sometimes a bit low. When you take the maximum of these noisy estimates, you're more likely to pick one that's currently overestimated just due to noise. This introduces a positive bias into the update target, which can propagate and lead the agent to prefer actions whose values are overestimated.
So it might think some actions are better than they really are just because of the noise in the maximization step.
Exactly. This led to techniques like double Q learning. The idea is to use two independent Q value estimates, say Q arrows Q. When you update Q, you use Q to choose the best action in the next state, finding A that maximizes Q euros A, and use Q to get the value of that action.
So you decouple the selection of the best action from the estimation of its value using two estimators.
Precisely. This breaks the feedback loop that causes the overestimation bias, leading to more accurate value estimates.
Clever. Okay, so we have MC, full episodes, actual returns, and TD, online bootstrapping. You mentioned bridging the gap between them.
Yes, that's where in-step bootstrapping and eligibility traces come in. These are ways to get the best of both worlds, creating a spectrum between pure TD and pure MC. Let's look at n-step methods first.
How do they work?
It's quite intuitive. One-step TD looks only one step ahead for the reward, and then bootstraps from the value estimate one step later. Monte Carlo looks all the way to the end of the episode for the actual rewards. N-step TD does something in between.
It looks n steps ahead.
Exactly. The n-step target uses the actual rewards for the next n steps, R euro plus R plus OR, and then it adds the discounted value estimate of the state reached after those n steps.
So it's a mix. N steps of real reward, then a bootstrapped value estimate.
Perfect summary. If n is 1, you get TD 0. If n is very large or goes to the end of the episode, you approach Monte Carlo. You're essentially choosing how deep your sample backup goes before you rely on an estimate. And empirically, intermediate values of n often perform better than pure one-step TD and better than pure MC. It's a way to trade off bias from bootstrapping too early and variance from waiting too long for the full return.
Makes sense. So n-step methods define this spectrum explicitly by the number of steps in. What about eligibility traces? How do they fit in?
Eligibility traces are another, often more computationally elegant, way to bridge TD and MC, especially useful for online learning. The core idea is to maintain a short-term memory trace called an eligibility trace, often denoted Z, for each state or state action pair, or for each parameter if using function approximation.
A memory trace, what does it track?
It tracks which states or actions have been recently visited or taken and were involved in recent value estimates. When a state S is visited, its eligibility trace ZS is incremented or bumped up. Then, over time, all traces decay exponentially, usually controlled by a parameter, lambda, where E is between 0 and 1 determines how fast the memory fades.
Okay, so recent states have higher traces. How does this affect the learning update?
When a TD error occurs at time t, the update isn't just applied to the state S. Instead, the error R is used to update the values of all preceding states S in proportion to their current eligibility trace ZS.
Whoa, so the error signal gets spread backwards in time?
Yes. It assigns credit or blame for the current TD error back to states that were visited recently, weighted by how eligible they are, how high their trace is. A state visited very recently gets a large share of the update. A state visited longer ago gets a smaller share because its trace has decayed.
And how does Lambda control this?
If E0, the traces decay immediately. Only the current state S0 gets updated. That recovers one-step TD. If E1, in episodic tasks, the traces don't decay within an episode. The error gets spread back almost equally across all previously visited states in the episode, making the updates much more like Monte Carlo updates.
So Lambda creates a smooth spectrum, just like N did for n-step methods.
Exactly. Intermediate values of Duke provide a blend between one-step TD and MC. The source mentions SARSA, which combines SARSA with eligibility traces, and Figure 12.10 shows it on the mountain car problem. Just like with NSTEP, intermediate values of OOV often lead to the fastest learning. Eligibility traces are a very powerful and widely used mechanism.
Okay, that provides a sophisticated way to manage credit assignment over time. We've covered model-free in detail now. We touched on model-based earlier. Can we combine them, get the best of both?
Absolutely. That leads us to integrated planning and learning architectures. The DINA architecture is the classic example here, covered in Section 7.
DINA Figure 8.1. How does it actually combine the two approaches?
DINA has several components working together. First, there's DirectRL. This is the standard model-free learning loop. The agent interacts with the real environment, gets real state action reward experiences, and uses this to directly update its value function or policy, like Q learning.
Okay, learning from real experience.
Second, there's model learning. Using the same real experiences, the agent also learns a model of the environment. It learns to predict what the next state and reward will be given a state in action.
So it builds its own internal simulation based on what it sees.
Exactly. Third, there's planning. This is where the model gets used. The agent uses its learned model to generate simulated experiences. It can mentally try out actions in states by querying its model. If I were in state S and did action A, what would my model predict happens next? Fourth, it applies the same RL update rules, like Q learning, to these simulated experiences. So it's learning from both real interaction and imagined interaction.
So the real experience serves two purposes: direct learning and improving the model. And the model then provides extra, cheap, simulated experience for more learning updates.
That's the synergy. Real experience is often slow or expensive to get, but once you have a decent model, you can generate tons of simulated experience very quickly. Planning allows the agent to perform many more updates per real interaction, potentially speeding up learning dramatically. DynaQ is the version that uses Q learning for both the DirectRL part and the planning part, learning from simulated steps. Typically, the planning steps involve randomly sampling state action pairs that have been previously experienced and updating their Q values using the model's prediction.
The blocking maze example, Figure 8.4, showed this working.
Yes, it's a great illustration. The DynaQ agent first learns the shortest path in a maze quickly, using both real steps and planning steps. Then, the environment changes, the short path is blocked, and a longer path opens up somewhere else.
What happens then?
Initially, the agent's performance drops. Its learned values and its model still favor the old, now blocked path. It keeps trying it. But through real experience, it eventually hits the block. This real experience updates both its direct Q values slightly, and, crucially, it updates the model. The model now learns that taking that action leads to the block.
And once the model is corrected,
the planning process kicks in again. Now, when the planning process simulates taking the action towards the old path, the updated model tells it about the block. Planning can then explore other options, like the new path, much faster through simulation, propagating the new value information quickly through the Q table. So the agent adapts much faster than a purely model-free agent that would have to physically explore and find the new path entirely through real interaction.
The integrated approach seems really powerful.
It is. And the source notes you can do planning with sample updates, like DynaQ, simulating one outcome, or expected updates, averaging over all possible outcomes predicted by the model, like DP. Sample updates are cheaper, expected updates are more accurate relative to the model, but costlier.
Okay, everything we've discussed so far, MC, TD, DINA, often implicitly assumes we can store values for every state or state action pair in a table. But what about huge problems? Robotics with continuous sensors, games like Go with astronomical numbers of states. Tables won't work.
Exactly. That's the curse of dimensionality. And that's where function approximation becomes absolutely essential. Section 8 tackles this. For most interesting problems, the state space is simply too large for tables.
So instead of a table, we approximate the value function using a function.
Precisely. We use a function with parameters, like VSE or on, QS, AW, where W is a vector of weights or parameters. The function takes the state E's and maybe action A as input and outputs an estimated value. The key is that the number of weights, WS, is much, much smaller than the total number of states.
And the huge advantage is generalization.
That's the magic word. Because the same weights W are used to calculate the value for many different states. When you learn something from experience in one state and update the weights, that update automatically affects the estimated values of many other, potentially similar states.
So learning transfers.
Yes. You learn about unseen states based on their similarity, as captured by the function approximator, to states you have seen. This is what allows RL to scale to massive problems. Without generalization, you'd be stuck back in the tabular world, needing to visit every state.
What kinds of functions are used for approximation?
Lots of options. Simple linear functions are common and have nice theoretical properties. Decision trees can be used. And of course, the big one nowadays is artificial neural networks, ANNs, especially deep neural networks.
Let's touch on linear function approximation first.
With linear approximation, the value is just a weighted sum of features extracted from the state, VSS. Here, XS is a vector of features representing state S, and W is the weight vector we learn. The crucial part here is designing good features. XS, they need to capture the important aspects of the state that allow for meaningful generalization.
What are examples of features?
Could be anything relevant. Polynomial combinations of state variables, Fourier basis functions, or things like tile coding. Tile coding, figure 9.9, 9.10, is quite popular and intuitive.
How does tile coding work?
You overlay the state space with multiple grids, or tilings. Each tiling divides the space into discrete tiles. A given state S will fall into exactly one tile in each tiling. The feature vector X is then typically a binary vector where components corresponding to the active tiles, the one S falls into, are set to 1 and all others are 0.
And the source mentioned using multiple offset tilings. That gives coarse coding.
Yes. By using several tilings, each slightly offset from the others, a single state point activates multiple tiles, one from each tiling. When you update the weights associated with these active tiles features, the learning generalizes to other nearby states that share some of the same active tiles. This creates a smoother generalization than a single, sharp-edged tiling. Figure 9.10 showed how multiple tilings lead to much better generalization and faster learning compared to a single tile.
Okay, and then nonlinear approximation, especially deep neural networks, that's where a lot of the action is now.
Definitely. Deep ANNs can learn extremely complex nonlinear mappings from high-dimensional inputs, like images from a game screen, to values or policies. They've powered successes like AlphaGo, but training them effectively in RL isn't trivial.
You need special techniques, like those used in supervised deep learning.
Yes, things like batch normalization to stabilize training, and deep residual learning using skip connections, figure 9.8, which help gradients flow through very deep networks, making them easier to train. These were crucial innovations.
So function approximation solves the scaling problem and gives generalization. But it's not all smooth sailing. It introduces new problems.
It certainly does. The biggest one, a really critical point, is the potential for instability, especially when you combine three things: bootstrapping, like in TD methods, off-policy learning, learning about a policy different from the one generating data, and function approximation itself. This combination is known as the deadly triad.
The deadly triad. Why is it so dangerous?
Standard TD methods with function approximation often use what are called semi-gradient updates. They calculate the gradient of the error, but they treat the target value, which includes bootstrapped estimates, as if it were fixed, not depending on the weights being updated. This works okay, and is even guaranteed to converge for on-policy TD with linear function approximation.
But off-policy is different.
Yes. When you learn off-policy, the distribution of states and actions you see from the behavior policy doesn't match the distribution you're trying to learn about for the target policy. When you combine this distribution mismatch with bootstrapping, where your target depends on your current flawed estimate, and function approximation, where updates generalize, you can create unstable feedback loops. Errors can get amplified instead of corrected, and the weights W can diverge, blow up to infinity. Baird's counterexample, figure 11.2, provides a clear visual illustration of parameters diverging under semi-gradient off-policy TD.
So the combination can just break the learning process. Are there ways around this?
Yes, it's a major research area. One direction is to develop true gradient methods that don't ignore the dependence of the target on the weights. These are often based on minimizing the mean squared Bellman error, MSBE. Algorithms like GTD2, TD with gradient correction, TDC, are examples. They offer better stability guarantees, especially with linear approximation, but are generally more complex. Another approach involves different objective functions, like minimizing the Bellman error, BE, which can also yield stable methods. However, minimizing BE doesn't always guarantee the best performance in terms of minimizing the actual value error, mean squared value error, MSVE.
So it's a trade-off between stability and performance, or complexity.
Often, yes. The key takeaway is, if you're doing off-policy learning with bootstrapping and function approximation, you need to be aware of potential instability and consider using methods specifically designed to handle it. Simple Q learning with a big neural network trained off-policy isn't guaranteed to work out of the box.
That's a crucial practical point. Okay, let's shift gears entirely. Section 9 introduced a different class of algorithms, policy gradient methods. How are these fundamentally different?
They flip the focus. Instead of learning a value function and then deriving a policy from it, like picking the max value action, policy gradient methods learn the policy directly.
So they parameterize the policy itself.
Exactly. The policy is represented as a function, as state, which gives the probability of taking action A in state lays. And this function has parameter state. The learning process directly adjusts these parameters to improve the policy's performance.
How do they improve it? What's the goal?
The goal is typically to maximize some performance measure, like the expected total reward or the average reward per time step. They do this using gradient ascent. They calculate how the performance measure changes as you tweak the policy parameters, and then they nudge in the direction that increases performance the most, the direction of the gradient.
What's a key advantage of learning the policy directly?
One big one is handling continuous action spaces. Think about controlling a robot arm. The joint angles are continuous. For value-based methods like Q-learning, finding the action A that maximizes QS can be really hard if A is continuous. Policy gradient methods can directly learn a policy that outputs continuous action values as long as the policy function is differentiable with respect to A.
And they inherently handle exploration.
Often, yes. The parameterized policy is usually stochastic. It outputs probabilities over actions. So even if one action has the highest probability, there's still a chance the others will be selected, providing exploration naturally. You don't necessarily need separate mechanisms like A-greedy, although sometimes extra exploration noise is added.
Do policy gradient methods use value functions at all?
They don't have to, but they very often do. This leads to actor-critic methods.
Actor-critic, 2 parts.
Right. The actor is the parameterized policy as A it chooses the actions. The critic is a parameterized value function like VSW or QSAW. It estimates values based on the current state or state action pair.
How do they work together?
The critic helps the actor learn better. Instead of the actor adjusting its parameters E based on the raw total return, which can be very noisy and have high variance, it often uses feedback from the critic. For example, the TD error, calculated by the critic, can be used as a measure of how much better or worse the chosen action A was than expected. This TD error signal provides a lower variance estimate of the advantage of taking action A, which leads to more stable and efficient learning for the actor's parameters.
So the critic critiques the actor's actions, helping it improve more effectively.
That's the intuition, yes. Actor-critic methods combine the benefits of direct policy parameterization with the use of learned value functions to guide the learning.
Okay, policy gradients offer a different approach, especially good for continuous actions. Let's switch tracks now to something really fascinating, the connections between all this computational stuff and how actual brains and animals learn. Section 10 covered psychology and neuroscience links.
Yeah, this is where RL feels less like pure engineering and more like a potential theory of learning itself. As we said earlier, the basic trial and error idea lines up perfectly with decades of animal learning research.
Thorndike's law of effect, Skinner's operant conditioning.
Exactly. Skinner showed how behaviors are shaped by consequences. And shaping itself, reinforcing successive approximations to a target behavior, is used constantly in animal training and has direct analogs in how we might set up reward functions or intermediate goals for RL agents.
What about simpler forms of learning, like Pavlov's classical conditioning? Can RL models explain that too?
They can, and quite elegantly. The source mentions the Rescorla-Wagner model from psychology. It was hugely influential because it explained things like blocking.
Remind me about blocking.
Okay, say you train a dog that a bell predicts food. The dog learns to salivate to the bell. Now, you present the bell and light together, followed by food. The dog typically doesn't learn to salivate much to the light alone. The Rescorla-Wagner model explained this by saying learning only happens when the outcome food is surprising or unexpected. Since the bell already fully predicted the food, adding the light didn't create any prediction error, so no learning occurred for the light.
Clever. But that model wasn't perfect.
No, it was a trial-level model. It couldn't capture fine-grained timing effects within a trial, or things like higher-order conditioning, learning about a stimulus paired with an already conditioned stimulus. This is where the TD model shines.
How does the TD model apply here?
The TD model operates in real time within a trial. Because it bootstraps uses its own predictions to update predictions, it naturally captures timing. It predicts that the value signal, representing expectation of reward, will propagate backward from the reward to the earliest reliable predictor. This naturally explains higher-order conditioning and also predicts that conditioned responses should occur precisely when the reward is expected. Figure 14.4 shows this beautifully. The TD models predicted value peaks right at the expected time of the reward, matching experimental data.
Wow. So RL models offer a computational basis for these fundamental learning processes. What about motivation?
In RL, the reward signal is the motivation. The agent is built to maximize it. This connects to psychological notions of drive and motivation. The RL state can include internal variables like hunger level. If the agent is hungry, food provides a higher reward, motivating food-seeking behavior.
And the distinction psychology makes between habits and goal-directed actions.
So that's another really strong connection. It maps very nicely onto the model-free versus model-based distinction in RL.
Huh?
Model-free RL, where actions are chosen based directly on learned state action values without explicit look-ahead, looks a lot like habitual behavior. Habits are often fast, automatic responses triggered by a situation. You just do them.
And model-based RL.
Model-based RL, which uses planning and simulates outcomes using a world model, looks like goal-directed behavior. It's slower, more deliberative, and sensitive to the current value of the goal. For example, if an animal learns lever pressing gives food, but then the food is made distasteful, outcome devaluation, a goal-directed animal will stop pressing the lever because it knows the outcome isn't desirable anymore. A purely habitual animal might keep pressing out of habit.
And RL provides a framework for understanding how both systems might exist and interact.
Yes, and neuroscientists are finding evidence suggesting these systems might be implemented in different brain circuits, like parts of the basal ganglia and prefrontal cortex, though the exact separation is still debated.
Then there's the dopamine connection. This seems like the most direct link.
It's arguably the most striking finding. There's compelling evidence that the firing rate of dopamine neurons in the midbrain, VTA and SNPC, closely resembles the TD error signal from reinforcement learning.
The same error signal used in algorithms like TD0, SARSA, Q-learning.
It appears so. Dopamine neurons fire strongly when a reward is unexpectedly good, positive prediction error. They decrease firing below baseline when a reward is unexpectedly bad or omitted, negative prediction error. And they show no change when a reward arrives exactly as predicted, zero prediction error.
That's incredible.
It gets better. If you pair a neutral cue, like a light, with a reward, initially the dopamine neurons fire when the reward arrives. But after learning, they start firing when the light comes on, the predictor of reward, and don't fire much for the reward itself, since it's now predicted. This is exactly how the TD error behaves as it propagates backward to the earliest predictor.
So a signal computed purely from computational principles in RL seems to be physically realized in the brain by dopamine.
It's a remarkable convergence. The leading hypothesis is often framed in an actor-critic context. The basal ganglia circuits might implement parts of the actor, action selection, and critic, value estimation. Dopamine delivering the TD error signal to these areas could drive the synaptic changes needed for learning both values and policies.
Does this link extend even further down evolutionarily?
The source draws a parallel even to bacteria doing chemotaxis, their run and twiddle behavior. They move forward, run, sense of the chemical environment is getting better. If yes, keep running. If no, tumble randomly, twiddle, and try a new direction. It's a simple trial and error strategy. Oliver Selfridge saw this as a basic form of adaptation. The source uses it as a metaphor. Maybe neurons or small circuits act like these bacteria, adjusting their connections based on local error signals, like dopamine, to optimize some local objective, contributing to the brain's overall learning.
Amazing connections. From bacteria to dopamine to complex learning, RL really provides a powerful lens.
It truly does, for both artificial and natural intelligence.
Okay, we've seen the concepts, the algorithms, the brain links. How has this translated into actual results? Section 11 looked at real-world applications.
Yeah, RL isn't just theory. It has a history of impressive applications, even going back decades.
Like Arthur Samuel's checkers program in the 50s.
A true pioneer.
Yeah.
It learned to play checkers very well by learning an evaluation function for board positions, essentially a state value function combined with search.
And TD Gammon in the 1990s, that was a big one for TD learning.
Huge. Gerald Tesoro's program reached world-class backgammon level using TD with a neural network. Crucially, it learned primarily through self-play, playing millions of games against itself. That's pure reinforcement learning.
Even IBM's Watson, the Jeopardy champion, used RL.
A key part of it did. While the core was question answering, Watson's strategy for wagering on daily doubles and Final Jeopardy was controlled by an RL system. Tesoro adapted his TD Gammon ideas to learn an optimal wagering policy, maximizing expected winnings under pressure. It often made better bets than the human champions.
So beyond games.
Optimizing complex systems is another area. The source highlights a DRAM memory controller, figure 16.3. The controller acted as an RL agent, learning a policy to schedule memory access commands, actions, based on the system state in order to maximize performance metrics like throughput, reward, while respecting hardware limits. It learned a better scheduling policy than human experts could easily design.
And then came the deep RL explosion.
Right. AlphaGo is the poster child. Defeated the Go world champion. It used a combination, deep neural networks to evaluate positions, value function, and suggest moves, policy function, trained initially on human games, but then massively improved via RL self-play, guided by Monte Carlo tree search, MCTS, for planning.
But AlphaGo Zero was even more profound.
Yes. AlphaGo Zero, figure 16.7, was a landmark. It learned championship-level Go, starting from nothing but the rules. No human games, no expert knowledge input, just the rules and self-play RL. It used a single deep network, providing both policy and value estimates, MCTS for powerful look-ahead search during self-play, and the results of the search and the game outcomes were used to continually train and improve the network.
So the search effectively generated better training data for the network, which then made the search better. A virtuous cycle.
Exactly. It was a beautiful demonstration of pure RL combined with deep learning and powerful search, bootstrapping itself to superhuman performance.
Any other cool examples? Robotics.
The source mentions learning to soar, figure 16.10. An RL agent learned to control a simulated glider using sensor inputs like vertical wind speed to find and exploit thermal updrafts to gain altitude. It figured out this complex aerodynamic control task entirely through RL, maximizing altitude as its reward.
Wow. From games to hardware to flying gliders, the applications are really taking off.
It's clear RL is a key enabling technology now.
Okay, let's bring this deep dive home. Section 12 touched on final thoughts and future directions. What are some of the big challenges still facing RL?
One huge one is reward engineering. It sounds simple, just to define a reward signal. But crafting a signal that truly captures the complex goal you want the agent to achieve without unintended side effects is incredibly hard.
Agents might find loopholes or exploit the reward in weird ways.
Exactly. The agent will optimize the signal you give it, which might not be what you actually wanted. Performance can be extremely sensitive to the exact reward definition. Getting the goal right is tough.
And safety, especially for real-world systems.
That's paramount. RL agents learn by trial and error. Exploration means trying things that might be unknown or potentially risky. How do you ensure an RL agent learning in the real world, controlling a car, a robot in a factory, managing infrastructure does so safely? Guaranteeing safety during learning, especially during exploration, is a critical open problem.
Looking ahead, what's the overall outlook for RL and AI?
The source is pretty bullish. RL, especially supercharged by deep learning, is seen as a fundamental driver of recent AI breakthroughs and likely to continue shaping the future, probably in ways we can't fully anticipate yet. The ability to learn complex behaviors from interaction is just incredibly powerful.
It's been quite a journey. We started with the core idea, learning to maximize reward through trial and error.
Right, then unpack the key components.
Yeah.
Policies, value functions, Bellman equations.
Tackled the exploration-exploitation dilemma.
Compared model-free approaches like Monte Carlo and TD, including SARSA and Q-learning.
And saw how n-step methods and eligibility traces bridge the gap between them.
Looked at combining planning and learning with Dyna.
Addressed the need for function approximation to scale up and the stability challenges it brings.
And explored the alternative framework of policy gradients.
Woven throughout were those fascinating links to psychology and neuroscience. Pavlov, Skinner, dopamine, habits versus goals.
And finally, seeing the payoff in real applications, from games to robotics.
It really is a rich and rapidly evolving field. Thanks for navigating us through all that complexity.
My pleasure. It's exciting stuff full of deep ideas and practical potential.
Which brings us to our final provocative thought for you, our listeners. Reflecting on everything we've discussed, the sheer power of systems learning complex skills just by maximizing a reward signal, but also the profound difficulty in defining that signal correctly and ensuring safety, especially during the inherently uncertain process of exploration.
What fundamental changes, perhaps beyond just tweaking algorithms, what shifts in how we design, test, and oversee these systems are truly necessary before we can confidently let powerful RL agents operate more autonomously in the complex, unpredictable physical world around us?
How do we balance that incredible learning capability with the need for robust safety and alignment with human intentions? That's the big question.
Something to definitely chew on. Thank you for joining us on the deep dive. We hope you feel better informed about the world of reinforcement learning. We'll catch you on the next one.